Okay. Well, we're starting 5 minutes late, but if all goes well, I can compensate for it by ending 5 minutes early. Because it's Wednesday and I'm just over it already.
Hump day.
What?
You said hump day. That'll do it.
Yeah. One thing is, my week is a two-humped camel with very high humps because on Tuesday and Thursday, well, yeah, you too, because on Tuesday and Thursday teaching till 8. Yeah. Okay. Get the right page here. All right. So now, between today and next week, and close out chapter 1 by spending time on the 3 essential PDEs: Laplace equation, then heat equation, then wave equation. So today, let's time on 6. Laplace equation, and the very closely related Poisson's equation. Well, really, because Laplace's equation is Poisson's equation with a 0 right-hand side. So Laplace's equation, Laplacian of u is 0. Poisson's equation is Laplacian of u is equal to f, although it's often written with a minus sign in case of Poisson's equation, which seems kind of odd because f can be literally anything. So you can just replace f with minus f. But there's actually a good reason for it. So this will be my first digression of a day. I'll try not to have too many. So an operator, L, for example, the differential operator, the Laplacian, and we see differential operators all the time when dealing with ordinary or partial differential equations, is positive definite if it has positive eigenvalues. Well, that's one notion of positive definiteness. So in other words, LU is equal to lambda U, where lambda is a number and positive. U is called an eigenfunction. All right, so operator applied to U is equal to number times U. So it's an eigenvalue eigenfunction relationship. An equivalent definition is this expression, which is equal to an integral over some specified domain, D, of u of x times Lu of x dx. So it's an integral over some domain, the appropriate number of dimensions. So like if we're dealing with a three-dimensional Laplacian, this would be an integral over some domain in R3. Also has to be strictly positive whenever u is a non-zero function. Because if u was 0, then certainly this whole thing would be 0. Now, this expression is called an inner product, something we'll be seeing from time to time. You're familiar with the and I think it's actually came up last time, dot product of vectors, so dot product of two vectors is a number. You multiply corresponding components and then you add them all up. This inner product is essentially the same thing, but you can think of each of these functions as like an infinitely long vector. What are you doing? You're multiplying corresponding values and you're adding them up, because what's an integral? A summation. Yeah. So it really is the same idea. Two ordinary vectors are orthogonal if their dot product is 0. Two functions are orthogonal if their inner product is 0. It's all the same. And some really snobby anal mathematicians will say, no, I shouldn't say these are equivalent, but they are. I mean, duh. And it helps students understand all the concepts if it's pointed out how they relate to each other. And in fact, unfortunately, only half of this class has been exposed to significant numerical linear algebra. You saw some, but that was a while ago, and not as in depth. But I covered a notion of a symmetric positive definite matrix, and that was like X transpose AX is positive. Dot product, inner product. You see it's the same kind of expression. Right. So again, it's all the same. And I'm going to show you in a one-dimensional case why we have a minus. And yes, it's a terrible digression on my part, but you get little tidbits from it that can help you. 1D case, the Laplacian operator is simply U double prime. So I'm going to look at the inner product of U with U double prime. And that would be the integral on some interval, AB of U of X, U double prime of X. And I'm going to assume Dirichlet boundary conditions. And what that means is U of A and U of B are both 0. So I'm going to rewrite this integral using integration by parts, everyone's favorite integration technique. So this would be the role of my U. Okay, bad notation choice, deal with it. That is your dV. So I would have U times V, the integral of this, which is U prime, evaluated at A and B, minus the integral of V, which is U prime, and du, which is also U prime. U prime of X squared dx. So, given the boundary conditions, what does this turn out to be? If I plug in the limits A and B, yes, it's 0, because U of A and U of B are both 0. So that's gone. Okay. So what's left? Minus the integral of something squared. I'm assuming U is non-zero, so this integral is going to be positive. Therefore, the whole expression is going to be negative. So in other words, Laplacian by itself is negative definite. It has negative eigenvalues. So that's why Poisson's equation is customarily written with a minus so that the operator featured on the left side is positive definite. There are many solution methods specifically designed for like positive definite matrices. So again, it's not a big deal, but knowing whether certain operators are positive definite definitely guides your choice of solution method, because certain ones are available to you that would not be otherwise.
So does that mean Laplace is negative definite?
Yeah, Laplace equation, yes. So if you leave it as is, and then you like discretize this to get like an AX equals B, where you have something over here to boundary conditions, then the matrix would be negative definite. But then, of course, you could always just negate both sides and make it positive definite. But, yeah. So, for instance, if I want to approximate solution to one of these, and I get some system of equations to solve, and the matrix, like if I go ahead and use the minus sign, the matrix is positive definite, and I apologize that not all of you would have a background to answer this, but if I'm solving a system that is positive definite, what's one of the approaches that I could use that I could not use in general? I know it's been a few months. Like, what's something that's specifically built for positive definite?
Start with an S.
What?
Start with an S.
No.
Start with an S in it.
Yes. But most words have an S in them. Actually, there are two methods that both start with a C.
A C.
Yeah.
Is it 2 words?
What?
Is it 2 words?
Well, yeah, I guess they both are 2 words. We're playing charades again. Numerical analysis by charades.
A method starting with a C.
Well, while you're thinking about it, I can see what I'm actually supposed to be covering. Oh, okay. It's like I'm getting the wrong pages. Okay. What?
It's something that Cauchy guy.
Koshi. As I told you literally an hour ago. No, not him.
I was like looking for like numerical analysis and
Give up. Cholesky decomposition. Well, I guess it's my fault because I remember several years ago when Amber Sumner took my numerical analysis class, and I got the evaluation at the end of the semester, and there was a comment that could only be from her. And she said, all the comment said was, when I think symmetric positive definite, I think Cholesky. Because I tried really hard to burn that into students' brains, that anything involving symmetric positive definite, that's something that's going to be useful. The other one is the conjugate gradient method.
that was like the last.
I was thinking that one.
Okay, well, next time, put it out there, because
I know.
yes, that is a flaw in all students, especially here in USM, that they would rather be silent than wrong.
And then record it and hear yourself wrong.
Okay.
Yeah.
Okay, so I realize that creates an extra burden, but I like it when students stick their neck out. So, because they may be wrong at first time or even the second time, but in time they turn out to be right. So keep that in mind for the future. But no, it's a rule. Never let them hear you. Just hoping it since I screw up at least once a day. Who knows how many flubs of mine are immortalized on YouTube for the world to see. I have like subscribers and stuff. So not many. I guess once my videos get like maybe 1 billion views, maybe I can make some money off of these. Okay. This is not the right page. Bye. I've covered that page. Now, Laplace's equation as used in itself, like I mentioned some time ago, modeling electrostatic potential, but also from other equations. So, for example, heat equation with a source term. So that's du dt minus Laplacian of u. Well, actually, I've been writing it the other way, but it's equivalent. Is equal to f, where f is some source term, like an external heat source. So as t goes to infinity, well, with heat energy, the solution will converge to something eventually. So then that means du dt is going to 0. So what we can do is, to understand the steady state solution, this is a very important concept in PDEs. The steady state solution that you will eventually converge to, what you do is to find the PDE for a steady state solution, you just assume that du dt is 0. So you just drop that term, and what do we have? Poisson's equation. Okay. So what I'm going to do is come up with a solution for Laplace's and for Poisson's equation. Okay. So, so to solve Poisson's equation, you use what's called a fundamental solution. Well, fundamental solution of this equation, Laplacian of u is equal to,
Dr. Language,
Yeah.
really fast, sorry. The Laplacian, the triangle that
Yeah.
signifies Laplacian.
Yes.
But which one is gradient is the upside down one, right?
Yeah.
Okay, never mind.
Now, this is equivalent to that if I square it. So
Okay.
this is another notation for Laplacian.
Okay, I was just thinking, there's nothing else that uses the triangle like that. It's just Laplacian.
I mean this triangle or the other one?
That one that you're pointing to.
Yeah, this is only Laplacian
Okay.
for PDEs. Whereas this without the square means like gradient or divergence.
Okay.
All right, and I need a minus. So I need a fundamental solution of Poisson's equation where the right-hand side is equal to this function, delta of x, which has a name, it's called the Dirac delta function. Now, the Dirac delta function is a very unusual function. And in fact, it's not even a function at all. It's called a distribution. So during my first year at Stanford, we had some particularly awful professor, who actually is a professor at NYU, and he was visiting Stanford, and we all hated him. He was just not a good teacher. And it was really amusing when I happened to be at a Sizzler restaurant where he was sitting nearby with his wife, who was also a professor at NYU, and their two young children who were behaving very badly. And he was trying to explain to them how to properly behave as if he was talking to adults. And it's like, this is not working. But it was amusing. So he tried to explain to us what distribution was, and he said he actually used a cat in the hat analogy. That he couldn't really, instead of explaining what a distribution is, like a formal definition, he'd explain what it does, like Voom and Cat in the Hat. He couldn't explain what Voom was, but he cleaned up everything. So that's what I'm going to do. The essential properties of this distribution. So delta of x is equal to 0 for non-zero x, and the integral over the entire real number line of a Dirac delta function is equal to 1. So you can think of it as having like some, if you were to try to graph this, it'd be like a function that has nothing in its graph except some infinitely high spike at x equals 0. So the effect of this distribution is that the integral over a whole real line of some function f of x times delta y minus x turns out to be f of y. So it turns out as if it's selecting the value of f at a particular point. And that's something that's going to be useful to us when we go ahead and solve Poisson's equation. All right, so like if you wanted to, you could think of the delta function as being something that looks like this, and then as you make it narrower and narrower, the spike gets taller and taller. And like, what would the limit of that be as the width epsilon of this non-zero area goes to 0? If you want to think, but except we're still thinking in terms of it literally being a function, but it's not really a function. It doesn't really obey the laws of functions. It's a distribution, whatever the hell that is. So in other words, I'm asking you to take these things for granted that these things work. But it does lead to a solution formula that can actually be used. Okay. Now, so what I want to do is solve this, and then we'll use that solution to write down a solution to Poisson's equation in general, for whatever f you have on the right side. Okay, so what I'm going to do is, since delta x is 0 for all non-zero x, that means that except at x equals 0, except at the origin, I'm actually solving Laplace's equation. So I can actually work with Laplace's equation first, and then work with that to get a solution to this. Dang, I've already burned half the class. Okay. Now, so what I'm going to do is work in it's really much like spherical coordinates in a way, that I'm going to work with distance from the origin. So I'm going to let r be my radial variable. So you think there's a magnitude of x. Or I often write it this way. I like using a double bar, indicating the norm of x, which is just going to be the square root of some squares. So this is Euclidean distance from the origin. Okay.
Euclidean what?
Euclidean distance. Yeah. So Pythagorean theorem in n dimensions. And I'm going to use this variable r to convert Laplace's equation into an ODE. So So the Laplacian is equal to sum of second partial derivatives of u with respect to each x variable twice and summing them all up. So like uxx plus uyy plus uzz. So I'm using this for however many variables I have. It doesn't matter. The procedure is the same. So I want to express this in terms of derivatives with respect to r to simplify this PDE. Because what I really want to do is, here I have a PDE in n variables. I want to boil it down to a PDE in one variable because that's an ODE. And that's something that can easily be solved. So for that, I need chain rule. So derivative of r with respect to each x. So that's going to be derivative of this expression actually I have to be careful about my notation. Here I'm taking derivative with respect to xi, but this is summing over all variables, so I use j inside the summation. Oh, and I need my 1/2, the 1/2 power. So I'm going to differentiate this using, well, regular differentiation rules. So I'm going to have 1/2 pulled down, and then I have this sum to the minus 1/2, so just plain old power rule. And then by chain rule, I need to take a derivative of what's inside. So that's now the derivative of xj with respect to xi, it's going to be what? These are independent variables. Most of the time, yes. Unless, what? Like if I'm differentiating x, y, and z, all with respect to x. So that's going to be 0 except when?
When x exists. Like when
Like derivative of y with respect to x is, derivative of x with respect to x is 1. Yes. So when j equals I, I'm going to actually get something. So I have 1/2, and then this right here with a minus 1/2, that's just x again, but in a denominator now. And then when j equals I, I'm going to get 2xi. The 2's cancel. So that is just going to be xi over magnitude of x.
That's only when j equals I.
Yeah, because otherwise derivatives, that's the only term that's going to produce something. All the other terms, you differentiate them, they'll be 0.
But still, no. Yeah, still the summation. So you have to do all the terms.
Yeah, you differentiate all the terms.
But all the other terms are 0 except
Yes.
for there's only a term when j equals I.
Yes.
Okay.
Okay, so we simplify everything and we get that xi over r. Questions about that differentiation? That's the thing about graduate classes. That's the point where you learn that every single nuance of everything you saw in Nova classes is actually needed now, long after you had a chance to forget it. And then I can do this again if I want the second derivative with respect to xi. So now I'm going to differentiate that using what rule? I'm differentiating that. Quotient rule. So that would be r times the derivative of xi with respect to itself, but that's 1, minus xi times the derivative of r, but that's what we just did. All over r squared. So that was a lot less painful than the previous, because we fell back to what we had before. So if we simplify, it's going to be 1 over r minus xi squared over r squared. Oh, r cubed, actually. Because r and then r squared. Okay.
So negative 1 or 1 over r?
Oh, that's a smudge. That's just okay. So now what I can do is express Laplacian in terms of derivatives of with respect to r. Okay, so please still be recording. Okay, so partial of u with respect to xi by chain rule is going to be u with respect to r times derivative of r with respect to xi. You think of the r's as like canceling. So that would be du dr times that, xi over r. Okay. Now, what I really need is not that. I need second partial derivative with respect to xi. But I can get that by differentiating this once with respect to xi. So, by product rule, I'm going to have, actually I'll use this, that's going to be easier. So u r xi r xi plus u r xi xi. So that's just what the product rule will give me. Differentiating one factor in each term with respect to xi. But now I need to flesh out what that actually is. Because I can write this. This is the same as u xi with respect to r. So that's the same as this with respect to r, because that's uxi. And then I still have that. And then I still have that. Okay. Now, although, wait, got that. Okay. Actually, I really want to do it this way. Okay. This is going to turn out to be URR, RXI, RXI again, so RXI squared. Okay. Oh. Yeah. Sorry, I shouldn't have written it this way. This did not help me. That's what I want. Because the point is, if I'm differentiating anything with respect to xi, I'm going to get a derivative of that with respect to r, which gives me a second r. And then this differentiation produces a rxi, but I already have one, so it's squared. Okay. So what I can do now is fill in what these are from over here. That's going to be URR, or I can write it this way, U double prime of R, because it's a function of one variable now, just R. And then this is going to be xi squared over r squared. And then I have U prime of R, and then this is written over there, so that's 1 over r minus xi squared over r cubed. All right. So questions about that?
Remind me what this is, like it's U xi, right?
Yeah. Yeah, that's what all this is here.
And this is we're still trying to solve Poisson's equation from
Actually, well, we're trying to express the Laplacian in terms of R so that we can solve Laplace's equation. Poisson's equation is the ultimate goal, but yeah.
Okay, alright, just making sure.
Yeah, but right now the main subtask is expressing Laplacian in R.
Okay.
So I've done part of it. This is part of Laplacian, it's one term. So now for Laplacian, which is the sum of all of these, is now going to be the sum of all of these. But the nice thing is, this part, like a u double prime of r and a u prime of r, those don't depend on I. So I can pull them out of the sum. So I get u double prime of r times the sum of all of these plus u prime of r, and then I'll sum these from 1 to n. All right. Now, things are about to get simpler, believe it or not. I sense your skepticism. Because the sum of all the xi squareds is r squared. Yeah, see, told you. So this sum is 1. So I end up with u double prime of r, and that's it for the first term. And then for the second term, I'm going to have u prime of r. Now 1 over r, I'm just adding that up n times. So that's going to give me n over r. And then here again, I have these numerators summing to r squared. So I'm going to get minus 1 over r. So that's my Laplacian.
So that's just Laplace.
Well,
Triangle U.
sorry, what?
That's just triangle U.
Yes, it is.
Laplace.
Yeah. So Laplacian of u is, to summarize, u double prime of r times, nothing, times 1, plus u prime of r times n minus 1 over r. And we want,
It's equal to 0.
so here we're solving Laplace equation, but can anyone tell me where this equation, where this PDE, well actually now it's an ODE, where is it not defined?
R is zero.
R equals 0. So this is valid on the whole n-dimensional space except the origin. So we're going to basically solving Laplace equation on Rn, cutting out the origin, but at the origin is where we want the right side to not be 0 anyway. It's going to be that delta function thingy, or distribution, or boom, or whatever. So let's focus on everything except the origin. Now, fortunately, this is actually a relatively simple ODE to solve. So u double prime is equal to, if I move this to the other side, I get 1 minus n over r u prime. Now, I'm going to make a little change of variable here. W equal u prime. So now I have w prime, which is u double prime, equals 1 minus n over r w. This is a first order ODE. And the sort of thing I would cover in like a class like Math 285 that half of you took from me. But I wouldn't expect you to remember how to solve this one. But it's a type of ODE that comes up often enough it's worth emphasizing. And frankly, it is easy to write down that solution. So W of R is equal to whatever function you have here, you take the exponential of the integral of it. And then there would be some arbitrary constant multiplying that. Okay. So
Yeah.
that kind of rings a bell, maybe. Yeah. Well, we saw a simpler version of this last time. I had y prime equals ky, and the solution was e to the kt. You're integrating that coefficient k. But here it's not a constant, so we have to write actual integral.
Is that like that word that starts with W in 285?
Wronskian
Wronskian.
doesn't play a role here.
Why would they call it W then?
Oh,
Because isn't it like a thing that you plug into or an ODE?
it's involved in a solution formula, but for a different kind of ODE. Yeah. Okay. Well, I did cover how to do second order ODEs, except not with a variable coefficient. And you could use try variation parameters, which does involve a Wronskian. Okay. So now I need to work out this integral. And actually I can work it out because I can pull out that constant, the 1 minus n, and I have the integral of 1 over r dr. What's the integral of 1 over r? Yeah, natural log. So I have e to the 1 minus n natural log of r times some constant. Forget about the constant for now. That exponential expression, how can I simplify that? Using properties of natural log.
Oh,
E natural log.
it's 1 minus
Just
n
R.
times r. Well,
No.
it's like, do you use logarithm?
Well, you do use property logarithms to rewrite this first, and then it becomes apparent how to simplify
Could
it.
you do e to the 1 minus n times e to the, no, never mind.
Okay.
That's wrong.
But Jessica,
You just get the 1 minus n times r up front. I mean, equal to that.
If you take the ln of e, then it cancels out the e and it pulls
The
power
e's
down.
and then you just have the
we do want the e and a log to cancel, but they can't cancel yet the way it's written. I need to do something about that 1 minus n that's
No,
dumbing
just
forward.
separate, like do e to the 1 minus n to the, like where you have to multiply ln of r times distribute that. 1 minus n.
Not quite.
Can you rewrite it using addition first and then pull it out of the one side?
Okay, apparently this one property has been forgotten. B ln A, same as ln A to the B.
Right.
Okay, yeah, so you n as the exponent up here.
And then you're gonna get
Yeah, then you,
r to the 1 minus n.
yeah, so e to the ln r to the 1 minus n.
But why can't you just do that?
What?
Why
It's
is
a
it?
different power.
What? Well, yeah, I'm just moving it up here, like I did.
Oh, yeah.
I sense skepticism.
I am skeptical.
Okay, but yeah, I'm literally doing this where b is 1 minus n.
Then you can just ignore the ln of r, like, and not count it as a power. Like, you can
Yeah.
just move part of it.
Well, he's just using the property first to rewrite it.
Yeah,
and
but
then
yeah, that's all I'm doing. So
Okay.
yeah, so I'm applying this. Take whatever's multiplying the ln and moving it to be the exponent of what you're taking the ln of. So fit it to this. And
B is 1 minus n.
yes, b is 1 minus n. It's like recasting itself. The role of b will be played by 1 minus n. So that there's no factor standing in the way, and now I have e to a log of something,
Oh, okay.
which lets me cancel them out.
Okay.
Well, that's what I was trying to do all at one time.
Oh, okay, yeah. Yeah, I think I was kind of jumbling what everybody was saying. Yeah, okay, so now we have a solution to the ODE at least. Oh, geez, running out of time. Dang it. Well, I knew it was going to happen. I digressed too much. So W, which is U prime, is equal to some constant times R to the 1 minus n. But the thing is, now we need to integrate that to get U. So U of R is equal to, and it turns out that what the solution looks like depends on the value of n. Because for example, suppose n is equal to 1. Well, then this goes away. I just have C. So I have CR plus D. It's just a linear function. Because it makes sense. Well, it's a Laplace equation. In 1D, it's second derivative equals 0. Well, the only function that has second derivative is 0 is a linear function. If n is equal to 2, so I have C times 1 over R. So I integrate that, and I get C times the natural log of R plus a constant. And then if n is greater than or equal to 3, then all those cases are treated the same. It's just power rule for integration. So I'd have C times R to the 2 minus n. And really I'd be dividing by something, because power rule, but I have an arbitrary constant, so I can just ignore that. Again, plus a constant. So that's what the solution has that form for the different dimensions. So it's interesting how the number of dimensions drastically affects what kind of function you have for the solution. But what we really want is to choose C and D so that at the origin, Laplacian of this would actually equal the Dirac delta function. Now, I won't go into detail about that because I actually looked up a proof, I Googled it, and it went on for pages and pages and looked really painful. But if you Google fundamental solution of the Laplace equation, you'd find it. But it was all about finding the constants. So to solve this equation, minus Laplacian of U is equal to the delta function. It's just a matter of choosing the right constants. So U of x, where x is in n-dimensional space, is so minus 1/2 absolute value of x for n equal 1. So in other words, d is equal to 0, and c turns out to be minus 1/2. And then we have 2 dimensions. It's minus 1 over 2 pi natural log of the absolute value of x, which is also r. So in other words, again, d is 0 and c is equal to minus 1 over 2 pi. And finally, a more elaborate expression here, 1 over n times n minus 2 times alpha of n, 1 over absolute value of x to the n minus 2. So d is always 0. So forget d.
Where did alpha come from?
I got to define that.
Okay.
Got a lot of board use here. Alpha of n is equal to the volume of a unit ball in Rn. So in other words, if it was n equal 3, it'd be the volume of a unit sphere, which is 4 pi. So volume of a sphere is like 4 pi r cubed or something. So it'd be 4 pi, if I remember correctly. And then whatever it is in higher dimensions, which I don't even know or care. Okay. So, unfortunately, dang, time is about to run out. So this fundamental solution of the Laplace equation. Okay. Actually, I'm going to change the letter here to a phi, because I want you to refer to my solution of Poisson's equation. So phi is my fundamental solution. Okay. So now I can use that to write down a formula for the solution of Poisson's equation. So I'll just do that real quick and then we'll have to stop. Unfortunately, that means knocking us behind, but I'll try to have a digression-free day for once. Monday. Okay, so solution to Poisson's equation, Laplacian of u is equal to f on the whole n-dimensional space. In other words, there's no boundary conditions to speak of. There's no boundary. Is the integral over the whole space of my fundamental solution at x minus y times f of y dy. And I'll show you real quick why that works. Because if I take a minus Laplacian of both sides, then I'm taking a Laplacian of whatever depends on x, which is only this. So minus Laplacian of phi, and Laplacian doesn't depend on shifts. Then f of y dy. But minus Laplacian of this is my fundamental solution. So it's a Dirac delta function. So that's delta of x minus y. Then using one of those properties of the Dirac delta function, it's selecting the value of f at x. So sure enough, minus Laplacian of u equals f. So that's the solution. Now, not very practical in numerical terms, because number one, we're on an infinite domain. And second, you get to evaluate this, you get to approximate this integral. But that's our start. But this is our starting point for being able to solve Laplace equation on more practical, like bounded domains and so forth. Okay, so well, actually, I'm about a half a page behind, so that's not so bad. I should mention phi is also known as a Green's function. You will want to time the semester to get into Green's functions. Did Dr. Zhu cover those in 606? Oh, okay. Oh, okay. Yeah. A Green's function is very much playing the role of like an inverse matrix, which no professor ever says, but to a professor with enough background should be obvious, but whatever. God forbid we make these things easier to relate to. Okay, but Green's function is used to write down solutions to various kinds of PDEs in terms of fundamental solutions like these. Dr. Chen, Dr. Tian, Dr. Zhu do work that numerical methods that involve fundamental solutions or approximate fundamental solutions. I think Dr. Chen's actually written a whole book on it. Okay, so I'll have to defer coverage of other properties of Laplace's equation to Monday, and then I'll have to haul butt after that to finish off this dang chapter. Because we still haven't gotten to numerical methods yet. That's going to be chapter 2. Okay, so I would encourage you, if you haven't looked already, to like this, again, the first homework problem is something that can be looked at. So maybe since our longer class is on Monday, we can take some time if you have any questions on that. So, okay. Good luck getting ticket boxing. Sorry.